and hopefully that's why you're here. Just a quick introduction to Stephane. Stephane joined us in 2008, if I'm not mistaken, coming from Yale, where he worked with former Robo grad Joel. Before that, he did his undergrad at the Ball. He has done a broad range of work since he came to St. Louis. He did things that maybe some of you don't know about, things like balance control for intelligent balance control for teleoperated mining machines in his early days, and has done lots of work on PV solving and all kinds of cool things like that. He's going to talk today about his work on algorithms and analysis of interactive learning, where the bulk of his work started here. He has a very diverse thesis committee to keep him honest. Sitting in the back to heckle is Chris Atkinson, who represents generalized learning control things. He's got an external member, John Langford. John coming from Microsoft Research, and a former senior as well. And Jeff Gordon, who's the other internal member from machine learning. Both of these guys are experts in machine learning generally, but particularly machine learning control, and also online learning. And general analysis. Okay, so with that, we'll let Stephane get started. I would ask that you hold questions, except for clarification questions, till the end, simply because Stephane's got a lot to say.
Thanks for the introduction. Okay, so basically this thesis is about how can we learn predictors to perform sequential tasks, like sequential predictions and decisions. And basically I'm going to show you learning algorithms that use interaction with the learner to provably learn good predictors that perform well both in theory and practice. So to start off, I'd like to show you a bunch of examples of what I mean by sequential prediction tasks. The first example might be imitation learning problems, where we want to learn how to perform a control task by watching an expert doing it. So for example, we might have this driving scenario where we want to train the car to drive on this road based on the observed camera image and want to predict to the steering that we should do to maintain the car near the center of the road. And so in this setting, we have an expert that can tell us which action we should do in any situation. So this type of problem is often addressed as a supervised learning problem, where basically what you can do is you just collect lots of training data while watching your expert perform the task. So you record, say, the images seen by the camera as the expert drives. You record the steering angles performed by the expert while you see those images. And then you just use your favorite supervised learning algorithms to train a predictor that can predict the steering given the image. The problem is if you do this kind of approach in practice, you'll typically get poor performance. So I'm going to show you a video that illustrates the problem. So here, I'm showing you an example of training data that we recorded in this racing game. And so this is a human who's playing, and what you could see is that all the examples are what you do near the center of the road. However, when we train on this data and we execute the learned predictor, what we can see is it's not perfect, it makes some mistakes, ends up in new situations like here near the side of the road, where basically it has no training examples of what to do. It doesn't observe that it needs to do, say, a hard turn to get that near the center. So that's why we get poor performance. So what goes wrong here? So basically the problem is that the policy that you learn, when it makes those actions or those predictions in the system, it changes the future inputs or observations it's going to get in the future and be evaluated as. So if, for example, our policy doesn't turn enough, it's going to end up in those new situations where it may not have observed what it should. And this makes learning very challenging because this fact that your predictions influence future inputs essentially break down all the main assumptions in statistical learning. So in particular here, we don't have IID training and test data. The training and test distributions are different, and this test distribution actually depends on the learned policy that you execute in the system. And formally, we can actually show that this kind of approach has very poor guarantees. So let's say you could learn some good predictor on your training data that has just some small error rate epsilon under, say, the expert, and you use that predictor to perform the task. So for t steps, you could encounter cases where the expected number of mistakes while you perform the task is as large as t squared epsilon expectation. So this is bad and much worse than the typical IID setting. So the IID setting, if you have to classify t-newt examples, you'd expect to make only t epsilon mistakes if you have such a predictor. But here, basically the problem is that as soon as you make a mistake, you could end up in new situations that leads you to make, say, mistakes until the end of the predictor. So that's why you pick up an extra factor. So what this says in practice is that even if you learn some predictor with low training error under training data, you won't necessarily get a good predictor to perform the task. And this mismatch between the training and test distribution that we observed in this imitation learning task also arises in many other sequential prediction tasks. So I'm going to briefly show you examples in other settings that I'm going to cover in this talk. So arise in structured prediction, in list optimization problems, and also for system identification. So for example, in structured prediction, we're going to look at problems like image labeling, where we want to learn a predictor that we iterate over the image to predict the object present at each pixel in the image. And we're going to try to learn predictors that use both features of the image locally around each pixel, and also previous predictions that we've made at nearby pixels of what objects were present to try to capture spatial relationships between the nearby objects. And so the problem is, if we use these features of the nearby predictions, these features actually depend on what predictor that we use to label this image. And the predictions that your predictor will do will influence the features that you use at your nearby pixels in the following prediction. So you can again get a mismatch between the train and test distribution because of that. That could lead to poor performance. And a recommendation task will have a similar issue. So here we'll look at problems like grass selection, where, say, given a robot manipulator, we want to suggest a small list of grass that is likely to contain grass that will be successful at picking up the object. And to construct those lists, we'll try to learn a predictor that uses both the features of the objects and obstacles in the environment, but also features of previous grass that we tried in our list and that failed. And this is important to use those features so that we can suggest, say, grass that are different and that are more likely to succeed. If you suggest grass that are too similar to previous ones that failed, they will also be likely to fail. And again, the problem is these features will depend on the predictor that we use, and the predictions that we do will change the future input features that we get as we recommend grass further down the list. In system identification, we again have another similar train test mismatch problem. So here we're looking at a problem where we're trying to learn a model of a dynamical system to perform a control task. And this issue arises because to collect data to fit our model, we'll have to use some kind of exploration strategy that will try different actions in different states to observe the resulting next states. This will give us examples of state transitions that we can use to fit the model. But then when we plan with that learned model, the resulting policy might go to, say, locations or states where we explored poorly and where our model might be bad. So this will lead to, say, poor decisions when we plan with our model in those locations. Okay, so what we can see is that there's all these kinds of different learning problems, like imitation learning, structured prediction, system identification, and recommendation problems that on the surface looks like typical supervised learning problems in that we can actually collect labeled data to train a predictor. But unlike IID supervised learning settings, we cannot learn to perform these tasks well by just obtaining, say, examples of good predictions. So the main problem that this thesis investigates is can we develop better learning algorithms for these types of sequential tasks? And I'm going to start by giving you some intuition on how we might be able to do better and the kind of learning strategy I'm going to present to you in the rest of the thesis at the time. Okay, so the main problem right now with this supervised learning approach that I showed earlier is that when we collect data by just watching the expert perform the task, we can never learn the sort of recovery behavior that we need to perform here to get back near the center of the road. Right? We never, say, collect training data in those critical situations if we observe a good expert. So the intuitive solution to this problem is to use what the learner has learned, so to interact with them. So say we run the current policy of our learner to go and collect additional training data in those new situations that the learner might encounter. And so our general approach will use this idea iteratively over many iterations, where we're going to interact with the learner, say by using his current policy to collect additional data, and then then using this new data, we're going to update our policy iteratively. So this is the general idea of our main approach as I'm going to present next. So now I want to make my thesis statement explicit. So what we show in the thesis is that for sequential prediction tasks, this kind of interaction with the learner is actually necessary to learn good and robust predictors. And what I'm also going to show you is that we can use no-regret online learning algorithms to obtain very practical and efficient algorithms to learn from these interactions, and also to obtain good performance both in theory and practice. So in particular, we'll be able to prove statements like this, that as long as there exists a good policy or predictor on our training data that we collect over the iterations, then this will imply that we'll find good policies to perform the task. Okay, so I'm going to start by showing you our main approach called dataset aggregation, and how we can use this approach to tackle imitation learning tasks, as I mentioned at the beginning. Then I'm going to show you how you can extend these techniques to tackle many other sequential prediction problems, like the one I just mentioned. And then finally at the end, I'm going to talk about some additional theoretical results in the thesis that indicates that this kind of interaction with the learner is really necessary to learn good predictors in general for these sequential problems. Okay, so imitation learning. So basically, as I said before, our approach used this idea of interacting with the learner over many iterations. The approach I'm presenting is called DAGGER, for dataset aggregation. And this is the way it proceeds. So at the first iteration, what you're going to do is exactly the same thing as the supervised learning approach I showed you at the beginning. So there's no interaction yet here. So we just observe that the expert performed the task. We record the images seen by the camera while the expert is driving, the steering angles, and then we learn a first policy by solving a supervised learning problem to obtain the first policy. But then what you do is you iterate. So at the following iterations, you're going to interact with the learner as follows. You're going to use the current policy of the learner. You execute this policy in the system. So this is like the computer is driving the car. And then as the computer is driving, the expert is going to provide the correct steering it would perform in each of the situations it encounters. So steering are not executed on the car, they don't control the car. It's always the computer's in control. So this will give us new data of, say, observed camera images under the current learner's policy, as well as the steering of the expert that we should do when we see those images. And because now we're actually running the policy of the learner, we'll be able to collect this additional training data that will tell us how to recover from mistakes the learner might make. This is how we'll be able to provide better performance. So what you do with this new data, you just add it with all the previous data you've collected at the previous iteration, solve a new supervised learning problem on all this data to obtain a new policy that you then use at the next iteration. So you just keep iterating like this. At each iteration, use the current policy to collect additional data about the expert's behavior, aggregate with all previous data, solve a new supervised learning problem to update the policy. And you do that for some large number of iterations n. So this is a very simple approach, and the very nice thing about it is that it actually has very good theoretical performance guarantees. So what we can actually show is that if you iterate this approach for long enough, you'll be guaranteed to learn some policy that when you use it to perform the task, its expected number of mistakes is going to be linear in the length of the sequence, t, the number of time steps. And its error rate is going to scale with the error rate of the best predictor in the class on the training data, so the aggregate data set that you collect over iterations. And then there's an additional penalty term that goes to 0 as we iterate more. So what this says now is that basically as long as there exists some good policy in your training data, you'll be guaranteed to find some good policy for performing the task. In the thesis, we actually show a much more general statement that says that we can also use any other no-regret online learning algorithm to update this policy at each iteration. And the way we prove this is by showing how essentially we can think of Dagger as running a particular online learning algorithm on a particular online learning problem. So the way you see this relation is essentially by saying that each iteration of Dagger can be thought as an iteration of online learning, where we have a learner that picks a policy that then gets evaluated on new examples that we collected at that iteration. And in online learning, what we're interested in is looking at the regret of the algorithm. And a no-regret algorithm, in this particular setting, what it means is that on average, the policy that is picked by the learner, when it gets evaluated on these new examples, is going to be as good as the error of the best predictor on the entire training data that you collect over all iterations. So what this says here is that if there exists such a policy that has low error on your training data, you'll be guaranteed to find policy that do well under their own trajectory, by the way we set out that problem. So what we show is that in general you can use this general interactive approach where at each iteration you just use your current policy to collect new data, then use that new data with a no-regret online learning algorithm to update your policy and just iterate like that. So you could use the gradient descent, for example, to update your policy, or any other no-regret algorithm. The data aggregation procedure that I showed earlier is sort of the special case where you use a fault deleter online learning algorithm, if you're familiar with that. So that's just a strategy that uses the best predictor so far based on all the data seen over the iterations. Okay, so basically our general guarantees look something like that. As long as you use a no-regret algorithm and there exists some policy with low error on the overall training data, then you'll be guaranteed to obtain a policy that has good test performance. Another thing we show in the thesis is that these no-regret online learning algorithms can be interpreted as having two key properties. One is they pick good predictors on the previous data that you've seen so far, the optimal one in the limit. And the second key property is that they generate stable sequence of predictors, in the sense that the addition of new data that you collect at each iteration In the limit, it will have an arbitrarily small change on the hypothesis that the learner is. So these two properties imply that you have a no-regret learning algorithm, and the implication of this result for a particular data aggregation procedure is that when you use a supervised learning approach on the aggregate data set, as long as a sequence of predictors that you predict is stable, because property won't always hold, you're going to be able to guarantee finding good test predictors, the predictors for control performance. This also illustrates an approach that might not work, for example, which would be to, say, update the policy in such a way that you always pick the best policy on just the new data that you collect at each iteration, because this would lead to a very unstable update of the predictor at each iteration. Okay, so now I want to show you some cool experiments that we did with this approach in imitation learning. The first one is this racing game that I showed you at the beginning. And this is the video of the performance with Dagger after training on 20 iterations. So here, each iteration was one more lap of training data. We're just learning a linear predictor in the color features of the image to predict the steering angle that we should execute. And what you can see is that with Dagger, we can actually learn a very good controller to perform this task. You can actually complete an entire lap without calling. So that's much better than the performance you saw at the beginning for the supervised approach. And so if we compare the average number of calls per lap with different methods, we can see that with Dagger, we actually learn very quickly a very good policy that almost never falls off the track. Here, that's just after 5 laps of training data. On the other end, with the supervised learning approach, even as you collect more data, you don't really improve performance. The reason for this is that all the new data that you get is always what to do near the center of the road. You never get to learn what to do in the critical situations where you're about to go off the road. So you never learn how to recover. You also do better than another previous imitation learning approach that has good guarantees. One of the major applications of my approach was to train a quadrotor to fly through the natural forest environments based on the observed image that it sees from its onboard camera here. So here the quadrotor just moves at fixed forward velocity, and we're trying to avoid any trees that's on the way. So here we're just extracting various features from the onboard camera image, and then try to predict the left or right velocity that we should perform to avoid any trees that we see. So this is also work that I've done in collaboration with many people here at CNU. Narek Kumar Shankar, Debarita Day, and Andreas Mandel, who was visiting last summer. They all contributed a lot to this project. Okay, so this is the learn controller with Dagger after 3 iterations. What I'm showing you at the bottom here is the commands that are executed by Dagger. Here you can see some features that we extract, like optical flow, which correlates with closer obstacles. We also extract edges to try to detect trees, which looks like tall edge that are vertical. And what you can see is that the controller that we learned is actually pretty decent at avoiding trees that are seen in the camera. And it also generalized to new locations. So in particular, in this area, we had never trained it to avoid trees. And you can still see that it can generalize from the features that it observes during the pilot demonstrations on how to avoid the trees in new areas.
The computation is on the board,
yeah. So we also did other experiments in Super Mario Bros. That are detailed in the thesis, and we again show improved performance of Dagger over other previous methods. Okay, so now that I've showed you how we can use technique for imitation learning problems, I want to show you how with the same technique or with some slight modifications, we can also handle many other different sequential prediction problems. So first one I'm going to talk about that I mentioned at the beginning is structured prediction. So in structured prediction, we have problems where the output prediction is very high dimensional. An example of that is image labeling task in computer vision. So for example, we have an input camera image and we'd like to predict the object at every pixel in the image. And these kinds of structured prediction problems arise in many different fields. There's many applications, natural language processing, computer vision, also computational biology. I'm going to focus my presentation on how to address these kinds of vision problems. But our approach would be able to tackle all these applications in other fields as well. Okay, so first naive approach that you might try to do this kind of image labeling would be to learn a predictor that say just looks at features locally around each pixel to predict the object present, so things like color or texture, edges, and so on. This would have the advantage of being very fast, so you could apply some maybe real-time in video, but it would typically get poor accuracy because it wouldn't take into account the spatial relationships that exist between nearby objects. So for example, if you predicted that the pixel next to you is a road, you're also going to likely to be a road, or you could be a car, something that's on top of the road. Right? We'd like to be able to take these spatial relationships into account to obtain better accuracy. So what people typically do to take into account these spatial relationships is instead to learn graphical models. And so these are probabilistic models that will assign a probability distribution over possible labels or labelings of the image. And given a new image, to predict the labeled image, you'll have to use some kind of inference like belief propagation, graph, or something like that. And so the advantage of this approach is because we're taking into account the spatial relationships between nearby objects, we can usually get good accuracy, but this inference procedure can be slow, so it can limit the applications of such techniques in real-time settings. For example, if we want to detect these objects in a real-time video observed by robot. So the approach that we consider instead is to try to learn a predictor that's applied sequentially over the image to label that image in a way that mimics the sort of same kind of inference procedure used by graphical model approaches. So we'll sort of mimic the same kind of belief propagation approach for inference. So basically this predictor, what it's going to use to make its predictions is going to look at local image features around each pixel, but also predictions made at nearby pixels to take into account the spatial relationships between nearby objects. So that way we can get good accuracy, but because we still only have to evaluate our predictions over the entire image, that will still be very fast and can lead to real-time applications. So actually this approach is very similar and inspired a lot by the work of Daniel Munoz, who's doing his defense on Thursday. And so if you want to see really cool applications of this kind of approach, also in real time, you should go see his defense Thursday. This is work I've done partly in collaboration with him, and I've focused mostly on learning algorithms to learn good predictors for this kind of approach. Okay, so that said, basically the idea that we're going to use to train good predictors that can use this, those features of the neighboring predictions effectively is to essentially view this problem as an imitation learning problem where we want to mimic some ideal predictor that always predicts the correct object present at each pixel in the image at any point in the sequence of predictions that we're going to do. So because we view this problem as just the same kind of imitation learning task, we can apply Dagger just as I've showed you before to handle these structured prediction problems. So here's how it would look say, for this imitation learning task. What you would do is you use your current predictor to perform the sequence of predictions over the image, label it at each iteration. So you would do that on your training images. As you do those sequence of predictions, you would record the features that you see. So that means the image features locally and also previous neighboring predictions at nearby pixels. And then you try to predict the correct object present at that pixel. That's defined in your labeled data. So you would add this data with all the previous data you collected at the previous iteration, and then solve the classification problem on the aggregate data set to update your predictor. Or alternatively, you could use any no-regret online learning algorithm to update your predictor based on this data. And here we have the same good theoretical guarantees because we just do this problem as an imitation learning problem as before, so the same guarantees hold. Okay, so we did some experiments on 3D point cloud classification. So here we're thinking of a setting where we might have a robot that has a LiDAR sensor. Through the LiDAR, it essentially observes a point cloud like this, and we'd like to predict the object present at every point in that point cloud. So here we're considering outdoor scenes that add 5 different types of objects, building, vegetation, ground, wires, and pole. And we just use local shape features around each point in the point cloud, as well as average nearby predictions. This is the execution of the predictor to classify the point cloud. And you can see that there's not much that changed after the second pass over the point cloud. So the predictions converge pretty quickly. And this is a comparison of the average test error on tests with different methods. And what we can see is that our approach is actually competitive with other state-of-the-art graphical model methods. We actually perform better than, say, conditional random field with belief propagation, and similarly to other M3N-based approach, or slightly worse. But these methods use a more sophisticated graphical inference procedure that seem to perform better for this type of task. There's other experiments in the thesis about handwriting recognition and also 3D geometry estimation in 2D images. And again, we can see that we achieve similar performance to state-of-the-art or slightly better.
You're talking just about prediction performance here, but
Yeah.
computation performance is probably also good.
Yeah. So in my code, my computations were not that well optimized, but in Daniel's code, you can get like these methods really fast. So in my case, it was like comparable, it was just slightly better than graphical model based approaches. Okay, so now I want to move on and talk about these recommendation tasks that I mentioned at the beginning, and how we can again use the same iterative and interactive procedure to learn good predictors for these types of tasks. So here we're considering problems like ad placement or news recommendation or this graph selection task that I mentioned at the beginning, where we have to predict a small list of items that maximize some kind of utility. In the graph selection case is we want to predict graphs that are likely to succeed at looking up an object. We have a limited budget, and that's we can only display 5 ads on the screen or try a few graphs to look at the object. And we're going to consider a utility that have this property of diminishing returns. And that's captured formally by submodularity, if you're familiar with that. What all this says is that basically, if we add an element in the list, its additional gain in utility that you get for adding this element can only decrease as the list gets longer and longer. And so to maximize this kind of utility, it will be important to trade off relevance and diversity. And in the case of this graph selection problem, what this means is that you need to predict graphs that are relevant for picking up different objects, but that are also different than previous graphs that you might have tried and that failed to get a higher gain by essentially trying things that are more different. Okay, so the main application I'm going to consider in these kinds of settings is trajectory optimization problems. So here we're going to look at the problems where we want to find a collision-free trajectory between the start and the goal location. And use some kind of local optimization procedure that, given some seed trajectory, tries to perform some small changes locally on that trajectory to obtain a collision-free trajectory. So these methods are really fast, but there are issues that they can get stuck in bad local minima that are not collision-free. And so in that case, we have to try to restart the procedure with, say, a new seed trajectory to eventually obtain one that's collision-free. That we can execute on the robot. So the idea here is I would like to optimize the list of seed trajectory that we send to our local optimization procedure to find a collision-free trajectory as quickly as possible. So here our budget is sort of represented by this time constraint. We'd like to say find a good trajectory as quickly, so by just optimizing with as few seeds as possible. And we'd like to maximize the probability that our list contains a seed trajectory that will lead to collision-free trajectory. Okay, so it's well known that to maximize these kinds of some modular utility function, a good algorithm is this greedy algorithm. It gives good approximation guarantees. So here, the greedy algorithm, what it does is basically just add the element to the list that has highest additional gain in terms of your utility. And the list that you're going to construct with this greedy algorithm is going to guarantee that it's within 63% of the optimal value of the list of the same size. One problem with this greedy approach for the settings we consider is that you need to be able to evaluate your utility function to decide which element has the highest additional gain. And this is not possible in the learning settings that we consider. So here, this utility function will be able to actually evaluate it only on, say, training environments. So in those training environments, we might know, for example, already which seeds lead to collision-free trajectories. But then what we'd like to do is actually learn a predictor that generalizes to test environments where we don't know already which seeds leads to successful collision-free trajectories. So we'd like to learn a predictor that can generate a good list for these test environments. There's been some prior work on dealing with these kinds of learning settings. The sort of state-of-the-art method before was from Devarim Tadei. We presented this approach called ConSecNet. It's basically using the same kind of greedy algorithm to train a list of predictors that, say, based on features of the environment, you evaluate each of your predictor, and these will tell you which element you should put in your list. And the way these two predictors are trained is just in sequence, where, say, the second predictor is trained to pick elements that as high gains as possible over the elements that are already picked by your previous predictor nodes, and just train them iteratively like that. And this can be done by solving a cost-sensitive classification problem. Okay, so instead, the approach that we present is going to try to learn a single policy to generate the entire list. And the advantage of doing that is that by learning a single policy, we can actually generalize the notions of relevance and diversity across different positions in the list, and be able to learn more efficiently with fewer training data. So we'll actually show that in the experiments. So here, the policy that we'll consider will look at features of the environments and also features of seeds that are already in the list to try to decide which seed we should try next if those failed already. And to learn good policies that can construct these lists, we can actually use a similar procedure, iterative procedure as well. So what we're going to do is at each iteration of training, we're going to construct lists with our current predictor on all our training environments. We're going to again record the features that we observe as we construct those lists. So these will be features of the environments and features of the elements in our list. And to these features, we're going to look at we're going to associate the additional benefits that we would get if we would add every other possible C trajectory to this current list.
I'm sorry, can you explain the right-hand side? There's two arrows underneath one arrow. Does that mean
So this is like a list of size 2. So as you construct your list, like after you pick the first element, you're going to generate your first training example where you add only one element in your list. Then as you decide the second element, you're going to add a new example when you add like 2 elements in your list and so on.
What's an example? What's a concrete example of this?
In the experiments, well, I'm going to talk about it in like 2 minutes. Okay. So, again, what you do is you just add this new data with all the previous data, and then you solve the cost-sensitive classification problem on all this aggregate data set to decide or to pick your next policy. And you just iterate like that. Or again, you can use any no-regret algorithm. And we can show that this approach, again, has very good guarantees. We're actually, given enough iterations of training and enough training data, we can guarantee that we're going to learn a policy that, for which the list it constructs achieves a value which is at least 63% of the value of the optimal list of policy, subject to an additional penalty term, which is just your average regret over the iterations. So in the limit of iterations, you actually guarantee the same performance as the greedy algorithm at picking, say, the best list of predictors. And so basically, this says that basically by just having this no regret property during training, we can guarantee a near optimal test performance. Okay, so we applied this learning approach to trajectory optimization, as I said before. We used the data set from the Quadributed day. There's basically 36 trajectories, 210 training environments, 212 test environments. Each C trajectory is represented by 17 features that change depending on the environment. And these features captures sort of the relative spatial properties of obstacles corresponding to where the C trajectory passes the environment. And so for the list features, we look at things like the minimum distance per feature between lists, between C's that are already in the list, or the average per feature distance. So this tries to capture whether you've tried C's, the trajectories that have very similar features to the C that you're going to try to have. Okay, so this is the result for this task. What you can see is that with our approach, we can actually learn much more quickly to predict good lists. So here I'm showing you performance as we increase the number of training environments. And what you're looking at is the probability of failure after trying 8 C's for a time. And so we do better than the previous ConSecUp approach, and we also do better than baseline regression approach that just sorts the C by predicted success rate. So this approach accounts for relevance, but doesn't account for diversity. For example, it might rank many similar C's that it predicts a similar success rate, all at the top, one after the other. So we have also done experiments in the thesis about graph selection, document summarization, and user recommendation. And again, in all these tasks, we actually show that we can achieve improved learning efficiency and performance. Okay, so finally I want to talk about the problem and system identification and how again we can use this same kind of learning strategy to learn good models in these types of problems. So here, what we want to do is learn a model, say, of a system that we can use for planning. So for example, if I want to learn a model of how the helicopter moves when you perform different actions in different states, and then use that model to plan to perform this desired trajectory near optimum. The sort of typical textbook system identification approach usually looks something like this. So you initially collect a lot of data of state transitions that you observe say while performing some kind of exploration policy that tries different actions in different states. Then you fit your model based on these observed transitions, and then you just plan with that learned model to obtain your policy to perform the task. So you optimize some given cost function that you want to minimize. In practice, engineers actually adopt much more iterative procedures like the Dagger approach I'm going to show you next. So the problem with this textbook approach is that it can suffer from this mismatch that I mentioned at the beginning. So this is illustrated here. We're collecting data by observing an expert who's performing the task. So the example is state transitions. We fit the model to those state transitions. And then when we plan with it, we slowly diverge from the desired trajectory and eventually end up in location where our model is really bad and just start planning very bad actions until we crash. So what we show in the thesis more formally is that even if you learn some good model at predicting future state transitions in your training data, and you obtain, say, a near optimal policy for your learned model, when you're going to execute that learned policy, you're not going to be guaranteed to achieve a good control performance. So to address this mismatch, you can again use the same kind of iterative and interactive learning procedure. So the way it works in this setting is at each iteration, you're going to use your current policy to collect additional state transitions. And you're also going to use an exploration policy to collect the same amount, equal amount of state transitions while using that policy. So this is going to give you new observed state transitions. You're going to add these new transitions with all the previous transitions you collected at previous iterations, fit a new model on that data, plan with that model to obtain your new policy. So here there's a particular distinction in this setting, which is that we not only need to use the current policy to collect additional data, but also an exploration policy to collect an equal amount of data at each iteration. The reason for this is that when we're planning with our learned model, we not only need our model to be good at predicting, say, future costs that our current policy incurs, but also future costs that other policies are incurring so that we can pick which ones are the best, which policy is the best when we do this optimization. Okay, with this approach, we can actually show much better performance guarantees. This is detailed in the thesis. And what we can actually show at a high level, what it says is that as long as there exists a model with low error at predicting, say, the next state distribution in your aggregate training data, and you use a no-regret procedure over the iterations to update your model, and at each iteration, you solve your model well, so you obtain a near optimal policy for that learned model, then you'll be guaranteed to achieve a good control performance at the test. However, our guarantees are actually relative to the quality of the exploration distribution or policy that's given to the algorithm. What this means is that if we're given, say, a very bad exploration policy that goes way out there, then there would be no way that we'd be able to compete against policies that can actually track well the desired trajectory. Like, we never get data, well, we cannot guarantee that we'll get data there, so we cannot compete with policies that might spend a lot of their time on those equations. So what this says is that ideally for approach, we'd like to have some exploration policy that's, say, a near optimal policy. So in practice, this could be obtained from an expert who can actually perform this. One of the main contributions of our approach in this setting is that its guarantees are agnostic. What this means is that the guarantees hold even if we cannot model perfectly the real system of the world. Most previous system identification methods, when they want to provide guarantees, they always assume a realizable setting where the class of model can capture perfectly the real model of the world. And the guarantees that we obtain are actually similar to previous agnostic model-free reinforcement learning methods. In the thesis, I also present an approach for doing a model-free reinforcement learning with a similar dagger procedure. I don't have time to cover that, but if you're interested, that you can look in the thesis, and I can also talk about it during your questions. The approach that we obtained in this thesis is actually very similar to previous iterative identification procedures proposed by Stephane Ross and Chris Atkinson in '97, and also by Peter Bill more recently. The main distinction compared to these previous methods is that our approach keeps this even balance between exploration data and data collected by our learned policy, and this allows us to get better guarantees in agnostic setting. Agnostic setting, it's really important to keep this even balance, because otherwise we could have an issue where our model is only able to, say, predict well the future cost of our learned policy, and does not predict well the cost of other good policies to perform the task. If we just collect further data by running the current policy. Okay, so we did some experiments for helicopter control that we learned to perform this kind of nose-in funnel maneuver that I showed earlier. This is the performance with our approach. So now when we're planning with the learned model with Dagger, we can actually track very well the desired trajectory. So this says we can actually learn a very good model of the system for performing the task. And unlike the approach I said at the beginning, where it was essentially diverging and eventually crashing the task. And that's after as many data collected. So here we compare the total cost of our learned controller as we collect additional training data with different approach. We can see that Dagger performs very well. It eventually reached the same performance as the optimal policy to perform this task. It learns faster than this textbook batch algorithm. And in this case, we could also see that the approach, the previous iterative approach from the build, was getting stuck in a bad loophole. It's not collect enough exploration data. We have other experiments in the thesis for learning to hover, and also for the inverted pendulums doing the task. Okay, so finally, I want to talk about some more typical results in our thesis that indicates that interaction with the learner is really necessary to learn good predictors for sequential tasks. So what we show is basically a lower bound on the minimum of number of interactions that you might need with the learner to obtain a good policy to perform the task. So in our analysis, we basically consider any learning algorithm that might operate as follows. It can take any training distribution that it sends to a learning oracle that then returns some predictor with epsilon error for this training distribution. It can do that repeatedly to train many predictors. And then it can combine those predictors in any way it wants to generate the policy to perform the task. So pretty much any learning algorithm you can conceive can be modeled by something like that. And basically the number of rounds of interactions that you need is this number of queries to the learning algorithm. So the question is, what's the minimum number of queries that you might need to guarantee finding a policy that has the order T epsilon test error to perform a T-step sequence? And our results actually show that you need at least order T epsilon queries to guarantee this performance in general. So this says that the number of iterations that you need will always at least scale linearly in the number or the length of the sequence. It also shows that you cannot create any learning algorithm that can provide this type of good guarantees without some kind of interaction with the learner for large enough T. Unless your predictor would be perfect. Yeah, that's true. And we also show that the lower bound is tight, and that we can construct algorithms that actually achieve it. But they're sort of theoretical, they cannot really be applied in practice. Okay, so in conclusion, I'm going to just go back to my thesis statement and show you how I proved my main statements in my thesis. So first statement was that interaction is necessary to learn good and robust predictors. I've showed that to you through the poor guarantees of the passive supervised learning approach, and also its poor performance in practice. And our lower bound proves that in general this cannot be possible, learning without interaction. And the second statement was that we can use no-regret online learning algorithms to provide good guarantees both in theory and practice. I showed that through the good theoretical and empirical performance of our approach. Also, it's improved learning efficiency. And in general, our algorithm is very practical because it's very simple to apply and implement. It scales to large problems because naturally online algorithms scale to very large problems. And it's also very modular, so you can plug in whatever your favorite learning algorithm is or wrap it around the existing software package. So in conclusion, this is the picture that you should have in your head. I've showed you all these kinds of different learning problems like imitation learning, structured prediction, system identification, and list optimization that cannot be learned well just from examples of good predictions, unlike IID supervised learning problems. But by using interactions with the learner, we can actually learn good predictors and performance tests. Thank you.
Okay, so here's how we proceed. We're going to go to the question period. The CME